Assalamualaikum and hi students. This is BEKG 2443, a lecture video for chapter 3, the vector calculus. So in this video, we will cover this LO, which is to evaluate surface integrals. In 3.5, we have parametric surface and its area. Okay, suppose that R is a two-variable function equal to x uv I plus y uv j plus z uv k. So previously we have rt equal to xt I plus yt j plus zt j, but now we have r uv, x uv, y uv and z uv. Is a vector value function defined on a region D in the uv plane. We look at uv plane now. Okay, the parametric equations for a surface is explicitly written down as x equal to x uv, two variable function of uv, y is equal to y uv, and z is equal to z uv as well. Okay, the parametric surface is the set of all points x, y, z in three-dimensional space, and uv varies throughout D. Okay, so this is the difference between line integral and surface integral. Right, for the example, give parametric representations of A, a sphere, okay, B, a cylinder, x square plus y square equal to 4, and C, an elliptic paraboloid, z equal to 5x square plus 2y square plus 10. Okay, so look at A first. Okay, for parametric representation of sphere, okay, we know that x is equal to A, any constant, sine, psi, cos, theta. And y is equal to A sine psi, sine theta, while z is equal to A, any constant A, cos psi. Okay, or we can write as x uv. X uv is equal to A sine u cos v, y uv is equal to A sin u sin v, and z uv is equal to A cos u. Okay, so this is the parametric representations for sphere. B, for a cylinder. For a cylinder, if we want to write x uv, so x uv will be, okay, since r is 2, so we have 2 cos u. Okay, y uv is equal to 2 sin u, and z uv is equal to v. Okay, and this can be written as r uv equal to 2 cos u I plus 2 sin u j plus z k. Okay, and for the last example, if we have paraboloid, elliptic paraboloid, z equal to, okay, so we let x equal to u and y equal to v. So our z now is equal to, substitute into x and y, so we have 5 u square plus 2v square plus 10. Okay, so this is few example for parametric representation that we will use in order to solve for surface integral. For the surface area, if a smooth parametric surface S is given by the equation, you have RUV, okay, x I plus yj plus zk, and uv is a subset of D, and S is covered just once as uv range throughout the parameter domain D, then the surface area, okay, the surface area of S is, to find the surface area, A is equal to double integration S surface, and then you have RU cross RV, magnitude of RU cross RV dA, where RU is dx over del x over del ui plus del y over del uj plus del z over del uk. We differentiate respect to u, and for RV we differentiate x, y and z respect to v. Okay. RU cross RV is equal to, okay, del X over del U, del Y over del U, del Z over del U, and del X over del V, del Y over del V, del Z over del V. The cross products for this is equal to, okay, the cross products is equal to this, I, J, and K. And then to solve for area, you need to find what is the magnitude, okay, the magnitude of this cross products. For the special case of a surface S with equation Z equal to fxy, if you can write Z in terms of x and y, okay, where x, y lies in D and f has continuous partial derivative. Okay, we take x and s as parameters, so the surface area can be solved by this double integration of R. Then you have square root of dz del z over del x square plus del z over del y square plus 1 dA. How to explain this? Okay, for example, if you have x is equal to x, and then y can be written as y, and z can be written as x and y. So you have z, x, y. Okay, so the Rx will be equal to xi plus yj plus z, x, y, k. Okay, so if we want to find Rx is equal to I plus, okay, we don't have j, then plus with del z over del x, k for Rx. And for Ry is equal to 0 plus j plus del z over del y, k. And from here, if you find what is the cross product for Rx cross Ry, okay, you have 1, 0, del z over del x, 0, 1, del z over del y here, and this is equal to negative del z over del x I, okay, minus del z over del y j plus k. Sorry, this is Rx cross Ry. Rx cross Ry, and the magnitude for Rx cross Ry is equal to square root of negative del z over del x square plus negative del z over del y square plus 1 square. And this is equal to square root del z over del x square plus del z over del y square plus 1. So that's why for the area, okay, we can write as this, as if we can write x equal to x, y equal to y, and our z is in terms of x and y. We have two examples. Okay, the first one, find a surface area of a sphere. Okay, for a sphere, we know our x, the parametric representation. Okay, x is equal to a sin psi cos theta, y is equal to a sin psi sin theta, and z is equal to a cos psi. Okay, so find what is del x over del psi. Del x over del psi is a cos psi cos theta. Then find what is del x over del theta, because we want to find what is the cross products of Rx with Ry, or del R psi and R theta. And then find what is del y over del psi, del z over del psi, del x over del y over del theta, and del z over del theta. Okay, so this is del x over del psi, del y over del psi, del z over del psi, and del x over del theta, del y over del theta, and del z over del theta. After that, you need to find what is r psi cross r theta. And for this, you need to substitute all these 9 partial derivative into this formula. Okay, and when you substitute this, you get r phi cross r theta is equal to a square sin square phi cos theta I plus a square sin square phi sin theta j plus a square cos phi sin phi k. Okay, so this is trigonometric cos square theta plus sin square theta equal to 1. Okay, from here. And after that, you need to find what is the magnitude for r phi cross r theta. Okay, so you need to square this a square sin square phi cos theta square plus a square sin square phi sin theta square plus a square cos phi sin phi square. Okay, and then you proceed with the expansion. Then from here, when you simplify, this cos square theta sin square theta is equal to 1. Okay, and then continue with here, and then you can factorize this, and then you get another sin square phi plus cos square phi equal to 1. And last, your magnitude for the cross products is equal to square root of a to the power of 4 sin square phi, and this is equal to a square sin phi. Okay, so from here you know what is your cross products of r phi and r theta. Okay, now you can find what is the area, the surface area for the sphere. Okay, so the surface area for the sphere is 0 to 2 pi, 0 to pi. Okay, the limit for phi and theta, and then you have the magnitude a square sin phi. Okay, and then do the integration respect to del phi del theta. So this one a square is the constant, so a square 0 to 2 pi integrate sine, you get negative cos phi 0 to phi d theta. And from here, okay, substitute theta, substitute phi equal to 0 and pi, you have 2, so 2a square, then integrate theta 0 to 2 pi. For this one, you have 4 pi a square. So the area is equal to 4 pi a square. Now we have another example for the special case. Find the area of the part of the paraboloid z equal to x square plus y square that lies under the plane z equal to 4. Okay, so you know z equal to x square plus y square, and then your z is equal to 9. So from here you have x square plus y square equal to 9. So you have a circle with radius 3. Okay, and then from z, find what is del z over del x. Del z over del x is 2x, del z over del y is 2y. Okay, since we can write z in terms of x and y, so we can use the special case formula. Okay, for the special case formula, we have a is equal to double integral. Okay, r limit is from 0 to 3 and theta limit is from 0 to 2 pi. Okay, and then substitute into formula. Del z over del x square plus del z over del y square plus 1. Then dA. dA is r dr d theta. Okay, try continue from here and see what the answer is. Okay, once you solve for the integration, double integration, you get the last answer is equal to 37, square root 37 minus 1 over 6 pi. Okay, you need to use the substitution here. 4r square plus 1 is equal to u. Okay, so for here, substitute x square plus y square is equal to r square. Okay, for the area. Moving to 3.6, we have surface integrals. Surface integrals of scalar fields. Okay, we have scalar and vector fields. For the surface integrals in which the surface S is given by z equal to gxy. The surface integral is, okay, we have double integral fxyz ds is equal to double integral fxy, and then your z is written in x and y, okay, in terms of x and y, and then you have square root of del z over del x square plus del z over del y square plus 1 dA. Okay, so before this, for the area fxy gx y is equal to 1. So that's why to find the area, you just do the double integration for this magnitude del z over del x square plus del z over del y square plus 1. But now, for surface integrals, we have a function. Okay, it's not equal to 0 anymore. It's not equal to 1 anymore. Okay, for those surface that are given by the parametrizations, okay, so you know these parametrizations, then the surface integral is, okay, double integration f ruv multiplied by magnitude of ru cross rv dA. Okay, so you know this ru cross rv. We derived this before. Okay. Okay, for the first example, evaluate double integral s x 3xz ds, where s is a plane, x plus 2y plus z equal to 4. Okay, so if we have this plane, the 3D, z, y, and x. Okay, so z can be written as x and y. So z is 4 minus x minus 2y. Okay, z is equal to 4, x is equal to 2, and y equal to 2 and x equal to 4. So you have this tetrahedron. Okay. And then from here, find what is your del z over del x and del z over del y, because we need to use this in the formula. Okay, so this is negative 2. And then for the double integration, okay, double integration, let's say this is our base. Okay, so we have double integration 3xz. Okay, substitute your z. This is your z in terms of x and y. So 4 minus x minus 2y. Okay, and then you have magnitude of del z over del x square plus del z over del y square plus 1. Then dA. Okay, so this is equal to double integration. Okay, we say 3. So you have 4x minus x square minus 2xy. And then for this one, 1 plus 4 plus 1 is square root 6. Okay, so since we decide this area, so we have dy dx, for example. And then we need to know what is the limit for y and x. Okay, so x limit, x is from 0 to 4. Okay, you better know this because we have discussed this in chapter 2, the whole chapter, for the whole chapter. And for y limit, y is from 0 to 2 minus 1 over 2x. Okay, and then proceed with the double integration. So the double integrations give you 16 square root of 6. Okay, so this is the surface integral for this plane, for this function 3xz scalar function. Okay, second example, evaluate the surface integral, double integral xz ds, where s is a part of plane x y z equal to 1. Okay, x y z equal to 1. So 1 1 1. Okay, z, y, and x. Okay, so if we write z in terms of x and y, so z is equal to 1 minus x minus y. Okay, and then we need to find what is del z over del x and del z over del y. Del z over del x is equal to minus 1 and del z over del y is equal to minus 1 as well. So for the surface integral, double integration, okay, x, and then you need to substitute z, which is 1 minus x minus y. Then square root of del z over del x square plus del z over del y square plus 1. Then your dA. Okay, so for this one, dy over dx, we can take dy over dx. Okay, for double integration, okay, double integration, we have x minus x square minus xy, and this square root is equal to square root 3. Let's say we consider dy dx. Okay, again, x limit is 0 to 1 and y limit is 0 to 1 minus x. Okay, from here, you can continue with the double integration to find what is the surface integral. Okay, so the surface integral is equal to square root 3 over 24. Okay, this is when we take z equal to 1 minus x minus y. Or you can do x or y, let's say y is equal to z, y equal to 1 minus x minus z. Okay, y equal to 1 minus x minus z. Okay, this is second alternative. So you can find what is del y over del x. Okay, this is negative 1, and del y over del z. Again, it is negative 1. Okay, and if you do the double integration, you have double integration. Okay, so you have x is x. You don't need to substitute the z because you don't need to substitute the y because you don't have any y here. So x is x, square root dy over dx square plus dy over dz square plus 1. And then do the integration respect to x and z, dx over dz. So for x and z, you have here z limit is from 0 to 1 and y limit is from 0 to 1 minus, sorry, x limit is from 0 to 1 minus z. Okay, if you do this, you have square root of negative square root of 3, 0 to 1, 0 to 1 minus z, x z dx dz. Okay, and from here you have square root 3, 0 to 1, 1 over 2 x square z, 0, 1 to z dz, and this is equal to square root 3 over 2, 0 to 1, 1 minus 2z plus z square multiplied by z dz. And if you proceed this, you have negative 3 square root 3 over 2, 1 over 2 z square minus 2 over 3 z cube plus 1 over 4 z to the power of 4, 0 to 1. And this is equal to, when you substitute the value of 1 and 0, have this is equal to 1 over 12, and the last answer is square root 3 over 24. The answer will be the same. Okay, and you can try for x equal to 1 minus y minus z. Okay, you have z equal to, first you have z equal to 1 minus x minus y. Second, you have, if you have y equal to 1 minus x minus z. Or last, you can have x equal to 1 minus y minus z. And the last answer should be all the same, square root 3 over 24. The last example for surface integral of scalar function. Okay, we have to compute the surface integral x square ds, where s is the unit sphere, x square plus y square plus z square equal to 1. For this one, you can't use the special case formula. So you need to know what is r. For this case, you need to know what is r phi cross r theta, the magnitude. And as we have derived this before, the cross products of r psi, r phi and r theta is equal to a square sine phi. Okay, so this is equal to a square sine phi. R cross products r phi and r theta is equal to a square sine phi. Okay, so you know this is equal to a square sine phi, and our a is 1. So in this case, the magnitude is equal to sine phi. Okay, so to find the surface integral for x square ds, this is equal to double integral 0 to 2 pi and 0 to pi for phi and theta limit, and then x is equal to sine psi cos theta square, and then ds is our magnitude. So magnitude is sine phi d phi d theta. Okay, again this is the x square, and this is our magnitude r phi cross r theta. Okay, and from here you may continue with the double integration. When you solve for the double integration, okay, use substitution here, u equal to cos phi here over here, and then the last answer you should get is equal to 4 pi over 3. Okay, here I use the trigonometric identity, where sine squared phi is equal to 1 minus cos square phi. And then okay, do another substitution for trigonometric identity. Cos square theta over cos square theta is equal to half 1 plus cos 2 theta, and you will get the last answer equal to 4 pi over 3. Last but not least, we have surface integral of vector field. Okay, a common type is the integral of the normal component of vector field. A closed surface is said to have a positive orientation if the unit normal vector points outwards. Okay, outwards, so it's a positive orientation from the region, while the negative orientation will be the set of unit normal vector that point in towards the region. Okay, outward and towards the region. Positive and negative orientation. The right hand rule is used, okay, to know the orientation of the, to determine the orientation of the vector field. Okay, if f is equal to, is written as pi plus qj plus rk, is a continuous vector field defined on an oriented surface S with unit normal vector n. Okay, n is the unit normal vector. Then the surface integral of f over s is equal to, okay, so the surface integral for vector field double integral f ds is equal to double integral fn multiplied by square root of del z over del x square plus del z over del y square plus 1 dA. Or we have double integral f ru cross rv, okay, dA, or equal to negative p del z over del x minus q del z over del y plus r. Okay, for positive n, okay, this integral is also called the flux. Okay, flux. When we do the when we find the surface integrals for the vector field, we find what is the flux. Okay, so you need to know, one thing you need to know is n. Okay, and for the positive n, it is equal to negative del z over del x I minus del z over del y j plus k divided by square root 1 plus del z over del x square plus del z over del y square. Okay, for n, positive n, so this one is for the positive n. So this give you the negative p del z over del x minus q del z over del y plus r. Okay, but if you have negative orientation, n is equal to, okay, for this one, you have del z over del xi plus del z over del yj plus k. Sorry, minus k. Minus k over square root 1 plus del z over del x square plus del z over del y square. And for this one, you have p del z over del x plus q del z over del y minus r. Okay, so for this formula, this is for the positive orientation. If you have negative orientation, you need to use this p del z over del x plus q del z over del y minus r. Okay, and n is equal to ru cross rv divided by magnitude of ru cross rv. Okay, this is the main things you need to know about the n. N is equal to ru cross rv divided by the magnitude of ru cross rv. Okay, let's see one example. Okay, find the flux of the vector field fx yz is equal to yi plus xj plus zk. Okay, over S, where S is the boundary of the solid enclosed by the paraboloid z equal to 1 minus x square minus y square, and z equal to 0. So z equal to 1 minus x square minus y square. Okay, we assume the orientation is positive since it doesn't say anything about the n. So z equal del z over del x is equal to negative 2x, and del z over del y is equal to negative 2y. And then z here is equal to 1 minus r square, since x square plus y square is equal to r square. Now, from the vector field, f equal to yi plus xj plus zk. Okay, the p is equal to y, q is equal to x, and r is equal to z. Okay, so substitute into the formula. So double integral s f ds is equal to, you have double integral. Okay, so 0 to 2 pi, the limit for theta, and the limit for r, x square plus y square is equal to 1. So limit is 1, 0 to 1. Okay, next we have to substitute negative p multiplied by d del z over del x, 2x. Okay, minus with q x multiplied by del z over del y, negative 2y, plus with 1 multiplied by k. R multiplied by k, so z. 1 multiplied by k, z. So r dr d theta. Okay. And then, as usual, you need to solve for the double integration. Okay, when you've done with the double integration, check the answer. The answer is equal to pi over 2. Use the substitution here, u equal to sine theta. Okay, so you have 0 here, and the last answer is pi over 2. Surface integral for this example. The last example in this video, we need to find the flux of the vector field fxyz equal to zi plus yj plus xk across the unit sphere x square plus y square plus z square equal to 1. Okay, so for this example, we cannot use, for the sphere, we cannot use this formula. So we need to find what is the double integration for f dot ru cross rv. Okay, so from the previous example, we know that the r phi cross r theta is equal to this a square sine square phi cos theta I plus a square phi sin theta j plus a square cos phi sin phi k. So from here, we know that r phi cross r theta, okay, with a is equal to 1, so it is equal to sin square phi cos theta I plus sin square phi sin theta j plus cos phi sin phi k. Okay, we have our r phi cross r theta, and then we need to do the double integration. Okay, double integration for sphere, unit sphere. We know that theta limit is from 0 to 2 pi and phi limit is from 0 to pi. Okay, and then substitute z. Okay, f x y z. Z is equal to cos, our FRT is equal to cos phi I plus sin y is sin phi sin theta, sin phi sin theta j plus xk. X is sin phi cos theta k. Okay, so this is our phi theta. And then we need to do dot product with our r, with the cross product of r phi and r theta. So cross product with sin square phi cos theta I plus sin square phi sin theta j plus cos phi sin phi k. Okay, so we have our d phi d theta here. So this is equal to, do the cross product. So I have here cos phi sin square phi cos theta plus sin cube phi sin square theta j plus sin square phi cos theta, d phi d theta. Okay, so cos phi, have cos phi sin square and then cos theta. So we have 2 of it. So 0 to pi, 2 sin square phi cos theta plus sin cube phi sin square, sorry, this is, there is no j, sin square theta, d phi d theta. And you can slowly do the double integration, solve for the double integration and check your answer with mine. Okay, as I do the double integration, solve for double integration, so from here, let u equal to sin phi. So for this one, I get equal to 0 because the limit is from 0 to 0. Okay, then proceed with this one. I have, I use the trigonometric identity. Sin square is equal to 1 minus cos square phi. Okay, and then use the substitution u equal to cos phi, and then by the substitution, I get the last answer equal to 4 over 3 pi. Okay, only for the sphere, we cannot use the simple formula. Okay, we need to use the other one. Okay, so that's all for this week video. For next week video, we have Stokes theorem and we have divergence theorem for the week 14. Okay, that's all for today. Thank you.